specimens that are loaded at lower stress levels, exactly as we've seen before. And when we are at high stress levels, we mainly have fiber pull-out. So probably we can, now that we'll talk about interrupted fatigue, using the same joke that we did yesterday, we can interrupt a bit for this first hour to take a break and resume in 5-10 minutes. What Professor Bedi, if you are still. We
can break for 5 minutes. Participants.
So we'll continue with this interrupted fatigue loading to see how the behavior of the material is when we interrupt the continuous fatigue and we unload completely. So in this case, again, we did the similar testing. And we created two SN curves. And in these SN curves, we can see that it is an obvious improvement of life. The interrupted loading, the black curve here, shows a significant improvement of life that is also more intensive or more obvious at the high stress levels than at the lower stress levels. We also did the similar analysis as we did in the previous work. We tried to fit the specimens of the two curves with a Weibull distribution. We've seen that it fits well. This is the analysis for the specimens at 53, so at this stress level here, where we had again more than 10 specimens to compare. And there you can see that the behavior is improved quite significantly. From 70,000 cycles, we went to 112,000 cycles. This is the average of the median, the median curve. And of course, as we said before, it becomes more significant when we analyze statistically, when we go to 95% reliability, for example. This increase is significantly more. But at least we see that we have 55% more lifetime for talking in a deterministic analysis. We have 55% more lifetime when we interrupt the fatigue testing. So again, discussing about the stiffness degradation, we see this recovery of stiffness, and we go down, and then we recover, and then we go down again, we recover, and we go down again. And this is a reason for this that justifies more or less this extension of lifetime. The same is observed when we see for the same stress level that continuous stiffness degradation under continuous fatigue, these red dots, are more or less always lower than the stiffness degradation for the interrupted fatigue loading. And the same comparisons for the failure images, the failure surface image, where what we can observe here and see as an effect of this interruption of load is this recovery that we were discussing before. And you see in the continuous fatigue, we have damage that is concentrated, and this is the same photos as before, concentrated and leading the material to failure. But in the interrupted fatigue, the damage progress in the specimen, even at high stress levels, here at 68 stress levels, is similar to the damage progress that we had in continuous fatigue at low stress levels. Is more spread, more distributed over the material. And this is, of course, the reason that makes the material sustaining more loads during the damage. And at low, as we said before, when we are at lower stress levels, we have similar behavior of interrupted fatigue and continuous fatigue. And this is the reason that if you go back to the SM curves, at low stress levels, we see that the difference is not so significant between the two loading patterns. The same behavior for the failure mechanisms. At high stress levels, we have mainly fiber pull-out, and at lower stress levels, we have fiber pull-out and fiber breakage. What is also different between the two is that in the interrupted fatigue, we do not observe this significant necking that we observed in the continuous fatigue at high stress levels. And as we mentioned before, interrupted fatigue loading is more performing, the material is performing more as the material performs in the continuous fatigue at low stress levels. So there we have the behavior for interrupted fatigue at high stress levels. We have the same behavior of the material as what we have in the continuous fatigue in low stress levels in terms of deformation. So to summarize this material number 2, as we call it, we've seen a lot of increase of the lifetime when we interrupt periodically the loading. This increase, in some cases, you remember this 2 hours creep load interruption. So even if we interrupt the load at the high stress level, sometimes we have increases because of this. And this is to a kind of trigger to make us question the characterization methods and the standardization. Because imagine now that you are discussing analyzing materials for a structure, and you want to investigate the material behavior to get material properties to use them for your design. And you follow the standards that say that you have to do a constant amplitude testing for a composite material to derive material properties. And then you use this material to a structure that is operating at interrupted loading. So actually what you do by doing this characterization with following the standards, you underestimate your material properties. So actually, what you do, if we bring it in the at the end of the day, you are suggesting a material that in reality can sustain more lifetime than the lifetime that you are designing. You are more safe in your design, but at the same time, you are actually over designing. You are making a material, you are making a structure that is more costly that it should be. With this testing also, we've seen that there are sufficient methods to identify the damage and to attribute the damage to failure. And I will summarize this. There's nothing else to say, I think, here. So I will continue with another material system. Now I will go faster and faster. And so this is a glass and carbon hybrid composite laminate. And we would like to see how this material performs. Again, here, I show the material characteristics. Carbon fibers with high modulus, carbon fibers with low modulus, and glass fibers were mixed together in different configurations, cause static and fatigue results. And the objective was exactly to investigate the hybrid effect. I don't know if you are familiar with this terminology. What is the hybrid effect in composites, either cause static or fatigue performance? But actually, is the effect of the mixing of two components. If we go back to the simple notation of a composite material, And if we, for example, have a stress and strain curve of a composite material, we know that fibers are very stiff and strong. We know that matrix that we are using is less stiff and more ductile. And when we mix these two, we have a material that might have a performance which is like that. So this is the composite, this is the fiber, and this is the matrix. So we do not expect the performance of the composite material to be better than the fiber or worse than the matrix. It should be in between. So this is defined, also the properties of this composite can be defined by the rule of mixtures. And the rule of mixture says that the properties of this depend on the percentage of these two materials. So the hybrid effect actually is an effect that we have in certain configuration of materials, that the properties of this composite that we are building sometimes override, become to the left, so become better. So the mix of two materials becomes better than the best one of the material used for the analysis, and this is done because of the actually the hybridization of the properties of the materials that are used for the mixing. In this case, what is the parameter for the hybridization? What is actually the difference that we have in these materials that we are using is that the glass fibers, actually, although they are less stiff and strong than carbon, they assume more strain up to failure. So they actually introduce ductility to a very stiff system. And this is the reason that actually this combination of glass and fiber, glass and carbon fibers, at the end gives a lot of benefits to a pure carbon composite material. So I'll go very fast. These are the material properties I will not discuss in details, only coming back to the initial considerations that we have carbon fibers that are very stiff and very strong. You can see the elastic modulus is 200 gigapascal, the high modulus carbon fibers with 500 gigapascal. And their strength, of course, is very high, around 3 and 4 gigapascal in strength. And glass fibers with a typical 76 to 80 gigapascal modulus, and of course less stiff. But the strain at failure, you see, the strain at failure is 2 to 4 or 5 times more than the strain at failure of the carbon fibers, and it's similar to the strain at failure of the epoxy resin, to have the compatibility between. So these materials that are used are typical materials used in civil engineering, mainly for reinforcement of concrete. So these are strips that are glued on concrete slabs to reinforce. Is there any question from anyone? Because I had some interruption. No, okay.
That was, I think, typically a disturbance. Somebody's mic was switched on.
Yeah,
So
only if there is a question, do not hesitate to interrupt me. So we did several combinations, material combinations, carbon and carbon. So carbon and carbon means layers of low modulus and high modulus mixing together. And then we did also combinations of glass and carbon with high modulus mixing together. We selected this high modulus exactly because of the difference of the strain. The high modulus is 0.5 strain at failure, glass is 3.7. So we mixed these two to investigate, as we said before, if there is any hybrid effect, actually to investigate the performance of this material, and if we could add or we can create ductility in the system. And this ductility, as you can imagine, we said we can artificially create ductility. The material itself is not ductile, but by mixing these two components together, we can artificially create ductility, and that's why we call it a pseudo-ductility. It's not a ductility of the material itself. So the setup is similar to what we had before. This is the same machine that we used before, but the chamber you see it down there now. We pushed it out of the machine. You can just take it out with some racks that we have here. And then the specimen now, it is outside of the chamber. The reason for removing the chamber was because these specific specimens are not heating a lot. So we could do fatigue testing at relatively high frequencies of 10 Hertz without the problem of the heating. We had a DIC camera to take photos and measure the full field strain on the surface, and we had also a high-speed camera that has been used to identify the failure modes. So the described stress strain curves here show exactly what we mentioned before about this pseudoductile behavior. And we see also that when we mix, so the black line is the carbon, so high and low modulus carbon materials. And this is the line with the glass and high modulus carbon material. We see that in both curves we have a pseudoductile behavior, which is more pronounced in this one, exactly because the difference between the strain at failure in this case is much higher. So this is a very significant effect, because this can help in structures. When a structure fails, the problem that we have with composite is composite materials are very brittle and fail without prior notice. So we can have a structure that works perfectly, if we call it like that, and then this structure fails without any notice. And if we have this behavior, we see that there is redundancy in the system. We start having some failure, but the structure does not fail at that point. It can continue in terms of strain and stress until very later. And this is an indication for us that something happens to the structure. The stiffness you see already is lower here. And we can identify the problems and repair. And actually, at the end of the day, you can even save lives with this by having this performance. So if we see these are the strain field measurements that we could get with the DIC during the loading, and we can clearly see the damage that is initiating and propagating in several locations. What is obvious here, this localized damage actually is the damage of the glass fibers. If I go to this specimen here, it's this part of the damage. So this is actually the bonding between the glass and the carbon fibers, and the eventual failure of the glass fiber layer. Do not forget that here we talk about unidirectional materials. The fibers are always along the loading direction. We plotted also.
I have a question.
Please,
can I?
Please.
Yeah, in the previous slide, previous to this, another back. Here, you see there is a bilinear behavior of the glass-carbon hybrid.
Mm-hmm.
Is this bilinear is because of the hybridization? Anything we can say? On this bilinear behavior on the glass-carbon hybrid?
Yes. So if I can assign this to this issue here you see also a bit of this bilinear behavior, and this behavior starts. So the change in the stiffness that you can observe in the previous photos and also in this one, is starting when you lose actually the contact between the glass and the carbon. Or the same when one of the layers starts failing. And this creates this damage. What is good here is that you don't have the linear behavior that leads your material to failure at a certain point without any notice of damage in the material. And this is the benefit of using these combinations to create this ductility in the system.
Okay, thank you.
So so this is until now we were discussing static loads, quasi-static loading. When we go to fatigue loading, again we observe the stiffness. Oops, sorry, I will show this again. We observe the typical stiffness degradation. Again here, if you see in fatigue, stiffness drops. We start initially, the first photo is here where we have a more or less intact specimen with only a few whitening on the glass, which is delamination, initiation of delamination. And then if we see a photo at this point where we have a stiffness which is already dropped, so this can be attributed to the bilinear behavior that we've seen before, more or less. There it is already a quite significant delamination between the glass and the carbon that causes this stiffness drop. This is the same that we've seen in the quasi-static loading. And of course, this delamination propagates, that the stiffness drops more and more, and it becomes now to the second stage of stiffness degradation, up to the final failure of the material. These photos were taken by the high-speed camera. So at the end, we have the final failure of the material due to this separation, if you like, of the layers at the end. So there is a small video, I hope it works, showing exactly, yes, the evolution of the damage with the loading and with the stiffness degradation. The failure is at around 20,000 cycles in this case. This was a test at 10 Hertz. So you see, we start already having some damaged fibers that are breaking, and then at the end, we have this explosive failure where already here now you can see at this point the carbon, so the high modulus carbon fibers that are in the middle already failed. So there is this ultimate failure of the material. This was a work that we did in collaboration with the University of Minho. We had a visiting scholar here that did all this testing and all this analysis. So this is another, no, it's the same test, no? Yes. So to summarize again the third material, we saw that we can use DIC to observe the fragmentation between the layers, the delamination, propagation in both materials. We've seen also that there is a nice effect of the hybridization. With this, we managed to have a pseudoductile tensile response, both in quasi-static and fatigue loading. Of course, again, this is a validation of what we've seen until now. You've seen, we checked 3-4 different materials, and always the typical laws, the power law formulation for SN curve is valid. This is the formulation that has been introduced more than 100 years ago. So the methods are practically available for any material system regarding the power law formulations for fatigue, regarding Weibull distribution for all the data, even strength data, stiffness data, they all follow more or less Weibull distribution. And for the specific material is that, so material 3, which is this hybrid composite, we've seen that we had damage that was localized and then initially localized and then distributed to cause delamination between the carbon and the glass fibers. And this is due exactly to the difference in the strain at failure of these two components. One is much stiffer than the other, and when we load, we lose somehow the compatibility between them. So then I will also explain a bit the behavior of structural adhesives. Go fast with these two last materials before the next break. So here we investigated structural adhesives. I suppose you know what is a structural adhesive. Is a glue that is used to do connections. So you see now I'm doing also the transfer from laminates to adhesively bonded connections that are used very much widely in engineering applications of any type, from aerospace to civil engineering to automotive. We always have structural connections that are made by adhesive, and actually they are very much preferred compared to bolted connections for a lot of reasons. There is huge list of reasons that that promote actually the adhesively bonded connections. What we did here, we did a lot of studies. If I want to talk about this material I can talk for hours, because we investigated structural adhesive for more than 10 years, and we have a lot of results on quasi-static fatigue experiments. And usually we try to investigate the fatigue performance, but also the durability, so the effect of the environmental conditions for these materials, because these materials are used in engineering applications that are used in the open air, so there you have effect of the environment. And we also try to investigate the effect of, here I wrote effect of voids, but actually it's the effect of the material itself initially on the properties of the adhesive, but also at the next stage on the properties of the adhesively bonded joints. To give you an idea, here I have some references starting from 2017 until even lately 2025. So it's already online, this last publication. And we also have investigations on structural adhesives starting in 2010 for the durability performance of them. So here I will come back to the discussion that we had regarding the standards. So ASTM standard suggests this specimen. Actually, this is what is called the specimen type 1. And it says also somewhere in the standard that in cases where you have tab failures, so failures that are initiated because of the gripping of the machine in this region, or you have other types of unwanted failures, you can use specimen type 2 or specimen type 4. Type 2 actually is the same as specimen type 1, but has more higher radius here and ends up with a smaller region in the middle to allow having a region here with lower area that will promote the crack at this region. And type 4 specimen is like the type 2 specimen, but it is shorter. So actually type 4, if I plot it here, it's something like this. So ASTM says that independent of the specimen type, you can have consistent results. And I keep this in mind. So how we prepare the specimens, we have either steel molds or plastic molds, and we can pour the material in the mold and carefully work with a spatula there to spread the material well. Another way that you can do is to prepare a plate with a certain thickness that you need, and then you can cut your specimens with a water jet cutting machine. And this is probably more accurate than this method, and it's also simpler to do. But again, they are both for both methods, there are advantages and disadvantages. So we used both, and we have results with both methods. So again, the setup is similar to what we had before, with the specimen mounted on the machine. This is a different machine. It's an electrodynamic machine. It's not a hydraulic machine. It's a new machine from MTS that can apply loads up to 3 kilonewton. So it's a small machine, but not with hydraulic pressure, with electrical motors. And again, here we use the DIC camera. We use the high-speed camera to take some photos of the specimen when it fails. So regarding durability, you remember we discussed before that composites are very hydrophilic, most of them, so they can absorb water. And imagine now that you have this adhesive system in a bridge over a river where you have a lot of humidity, so water can be absorbed. And we've seen that water in this material is saturated when it reaches around 3.5% in weight increase. So there, after this time, for this testing program, we also did desorption. So we tried to take water out. And then we have 3 types of specimens that you can see here as dry. So those specimens that are fabricated in the lab and were not immersed in water. We have the wet specimens and the dried specimens. So those that were saturated and then dried under a specific protocol that we followed. So if we jump to the results, we see that, for example, here you have the blue ones that are the dry ones, the wet ones, so that those that were immersed to water are the green ones, and the dried ones are the red ones. And the curves that you see here are the 5 and 95% curves that I drew based on the ASTM suggestion. So actually these curves every time show the range where we can expect 95% of the specimens of each class to fail. And what we can observe here is that the dried specimens are the best among all. So those specimens that were wet and then dried are the best among all. And here is the conclusion that we ended up in this case is that this drying procedure allows the plasticization that is happening to the material due to the water intake to actually coming back always to the same discussion that we had before. There is a region here that is caused by this plasticization, and this helps in the delay of the failure of the material. So we've seen that this helped in the static loading, and this helped also in the fatigue loading. So we also did another investigation with the same material, where we tried to check which fabrication method is the best. You see, usually these adhesives are also called cold curing adhesives because they allow their use in open air applications where you don't need to heat the material. You just pour the material, you know, mix the base resin with the catalyst, the hardener, and then you let the material there to cure. And we know that the material needs some days, 7-10 days. It's like concrete. Concrete stiffens in 28 days. So adhesives are also stiffening. So they're getting cured, polymerized in more than 7 days. This is what is written in the data sheets. But then what we observed with the investigation of this investigation that I showed in 2017, that the material behavior is developing also during time. You can have increase of the properties even in the first year, a year, not days, of the adhesive during operation. So here we try to see if it is probably better to do some post-curing during fabrication to help the material achieving the maximum the maximum properties faster. So we did 4 different curing conditions for the fabrication. The reference specimens, business as usual, no degassing of the specimen, 7 days in the lab, and then no post-curing. Then we had this R20 series specimens where, again, we didn't do any degassing. So we mixed the specimen and we let the air in the specimen. 7 days curing in the lab. And then we had the post-curing at 90 degrees for 30 minutes after these 7 days. Then we had the V. V means that we had degassing for the specimens that were 7 days left in the lab at 20 degrees, so V20. And then after 7 days, we had the degassing. And then we have this V90 that was mixed, degassed, and without any time in the lab was post-curing directly at 90 degrees after casting. So we did tests for these specimens and causostatic and fatigue. A very interesting result here is that fatigue results can again be fitted by these typical SN curves that are defined by ASTM. Here you see the linear fitting, linear regression recommended by ASTM 739. So again, we validate that we can use these fitting methods for these materials. And if then we go to compare so again, validation of viable fitting for these results. And then if we go to compare the behavior, we can see that the reference samples are the lowest, showing the lowest fatigue performance. And this is attributed to the post-curing. You remember before I said that the specimens are continuously increasing their properties even up to a year. So these reference specimens, we expect that if we test them again, if we have a sample of specimens and we test them again after a year, they will show performance that will be relevant to the other lines that have specimens, corresponds to specimens that have been already post-cured. So the post-curing helps, and we've seen that the post-curing helps when it is not immediately after mixing. So the green one is the V90. You remember V90, we mixed and then we post-cured directly. And this seems that it's not so beneficial as is the performance of these red ones, where we mixed, we let the material cure at room temperature, and then we post-cured after these 7 days. So the best performance that we investigated for these materials is the one that has been given by these V20 specimens. We also continued. Sorry?
Is this tension loading?
This is tension, yes. Tension is, I think it was written here, it's tension at 0.1.
Okay, thank you.
Sorry, I didn't mention, you're right. It's always tension at 0.1.
Okay, thank you.
There. No, it was not mentioned, you're right. So we continued the investigations to see the sensitivity of the boundary conditions, the specimen alignment, and we've seen that it is very, very significant to be careful when we create first of all, when we make the specimens, when we put them in the machine. What I saw here is actually these are DIC measurements of the strain caused in the specimen during gripping. You see, these are the grips of the machine, the specimen in the machine, and the strain. So the two first on the left, they are relatively good. The third one shows stress concentrations. And this might happen. This is a result, we know specifically for this specimen, but these are results that are happening because of the misalignment. Imagine you have a specimen, you put 2 tabs. If one tab is misaligned a bit because you put more glue and you didn't press well, so the specimen is like that. When you close the machine, this causes stress concentrations. If there is a gap in the glue, that you put between the specimen and the tub, then this again can cause stress concentrations. And this can be significant, can cause a lot of tub failures in the material. The second thing that we observed is that is
Yes, I have a small query from
yes,
my
please,
side.
please.
Yeah, like this tab failure and temperature rise in the tabs. We have seen that this phenomena is very, very persistent, specifically in materials which are having very high stiffness. We were testing few samples of very highly stiff glass fiber composites for wind turbines, and then we observed that most of the samples are failing in tabs. The failure region is the tab region in almost 90% of the samples with too much of temperature rise. I have the data also with me, which I will share maybe tomorrow. So, is there any? There are many explanations for this. That why the temperature rise and the failure is tab dominated. In that particular region itself, the failure is happening. But anything that you can comment upon, specifically for materials which are very stiff.
Yes, the stiffness, the stiffer the material, the more brittle it is.
Yes, that's right.
So this means that if you have a stress concentration, it's more significant for the material. If the material is ductile, then it can absorb somehow. It can dissolve this stress concentration. But if the material is stiff, then you have these problems. In our case here, the material is quite stiff. It's quite brittle. I wouldn't say it's stiff. The stiffness of this adhesive is around 5-6 gigapascal, but the behavior is very, very brittle. So that's why we've seen a lot of tub failures, and this is why we started investigating the reason for these tub failures, and we ended up to see there is a publication from I can share with you later on. It was in the slides. This publication from Peresul in 2021, where we specifically investigate this effect of we manufacture specimens with artificially misaligned tubs. We misalign the tubs already, and we've seen that if you glue the tub, even for 1 degree, it doesn't need to be really misaligned. If you are not careful with the tub, then you increase your potential for tub failure very a lot. The other point is the gripping pressure. How
that will be also higher for high stiffness material. The gripping pressure will also be high.
Exactly. If you don't press highly, if you have a very stiff and strong material, and if you don't press here, it will slide. You will never be able. So there again, it's additional efforts that you have to attribute to find gripping solutions that allow to transfer the load correctly. I will tell you what we did once. We were testing wooden specimens, and I mean this type of wooden specimens, typical dog bone specimens of wood. Okay, my drawing skills are not better than on Monday, but so what we've seen is that we had always tub failures, and then what we did, we kind of invented methods. So the specimen size for us was not the specimen size that was defined by the standard, but then we made the specimen that was like that, more or less.
Yeah, non-standard samples is also
yes. So we made a specimen that was like that with huge areas on the tub, so that there, what does it mean? That if you press here, you can transfer, because the tub, the grip transfers the load in a shear. So there you need a lot of area. The more area you have there, the less stress concentrations you have. So the standard might tell you, okay, you have a specimen of typical dog bone specimen of this type. But in this case, it might be that this area is not enough. If your specimen is stiff and strong, this area is not enough to transfer the loads. So you need to increase this area artificially yourself, of the specimen itself, to allow the transfer of this shear loading to the specimen correctly and without any specific concentrations.
I think the gauge length also plays a role in this.
Of course.
Now working with smaller gauge length for high stiffness, very small.
Of course, you will see also the comparison between the type 1, type 2, and type 3 specimens that type 4 specimens that we did.
Okay.
So here, again, the alignment plays a significant role. We've seen that if there is a slight misalignment of the specimens, like what we have in the middle or on the left, we had a kind of bending in the specimen, and we had always a small piece that was coming out of the specimen during failure. There is a footage here. So this is a high-speed camera measurement. You see the specimen on the right hand here. There is always this small piece that comes out. You see, probably I can let it run. This is a failure of the specimen, and this exactly what you see here on the right hand is exactly this effect of the misalignment. So, as I said before, we investigated the effect of the three different types. This is specimen type 1. This is specimen type 2, so the same length of the specimen but thinner. And this is specimen type 4, which is the same thin as type 2, but shorter. And we did a lot of fatigue testing for this. And we tried to reduce what you see here cleaned. We talk about data sets where we censored all the specimens that were failed at the tabs. So no, we only kept what we call the good failures. And we plotted this in fatigue SN curves, the stress and the SN plots. And we did also fit viable distributions. And we've seen that there is an obvious and very, very significant trend to show that type 4 specimens that are shorter and thin are better than type 2 that have the same thickness. So there is no size effects in this case. And both are much better than the specimens of type 1. And here is the big question. ASTM says, whatever specimen you take, if you have a good failure at the middle, as we have here, you should have the same results. And what we've seen is that we don't have the same results at all. And if we compare here even the average values, the type 1 gives around 52 megapascal as the best probability at failure, and type 4 specimen goes to 62. So this is more than 20% different properties estimated only by changing the specimen type. Although all of them are standard specimens, theoretically, someone can use one or the other and deliver design data for commercial applications, for commercial reasons. So this is the paper that I told you it's published right now. To my understanding, this is a very significant finding because it actually questions the standards and explains completely clearly that we should not take the standards as a book of that we have to follow without second thoughts, without consideration about the application of these results. And we should always think ourselves how to improve the experimental procedures to avoid having, as we said before, falsified results. We did also a bit of analysis to show why this happens, and probably it is because of this stress at the end. We've seen that at the region of the failure, the stress for all of them is always the same, and it is always with a let's say consistent area that we have a good uniform stress distribution. So there is no problem with any of the specimens in this sense. There we also we also investigated the frequency effect. As we said before, the higher frequency, the better it is, as long as you don't heat up. So here we did this. We've seen that even at 40 hertz, 40, it's a very high frequency. Even 40 hertz did not cause significant heating. Actually, it helped a bit. You see, with the frequency increase, we can shift a bit the curve to the right. So we can increase a bit the performance. What was the problem that tells not to use this 40 Hertz for the specimens is that by using 40 Hertz, we increase a lot the tab failures. And this again is because of the loading rate that it's very high. So the tab failures are becoming much more frequent in this sense. So to summarize again, material number 4 is that we used again DIC is useful for giving significant information. The methods that are used for simulation are again valid, viable, symbol curves are valid. For these specimens, and we have understanding that for other specimens, the specimen type, so the considerations from the standards have to be thought twice before followed, and we have to be very careful when we prepare the specimens. We've seen that the preparation of the specimen itself, the geometry, the alignment in the machine is very significant and can affect the results a lot. So if you don't mind, Raman, I can go very briefly in this before we do the second break. We already passed a bit of time as you advise.
It's up to you. We can take a break, or you can continue for some more time and then take a break.
As you wish, because this is for me the last material that I will describe, and then I will describe a bit the methods that we have for the statistical analysis for the fatigue data. So slowly I will go to the modeling in this sense.
Yeah. So you can take time. No issue.
Okay, so let me go. I will go very fast. Yes,
yeah.
I will go very fast. So here we talked about adhesives, we talked about composites, and now is when we mix these two and we make adhesively bonded joints. And there we did again a lot of investigations in the past. And of course, the set objectives there were again the fatigue and fracture performance. Now we are also introducing the fracture behavior of the materials. In terms of long-term performance, so which means durability, and of course all these investigations are for achieving finally a modeling of the material. So in this case, here I saw a testing program with double lap joints. This is the geometry, and this is the focus on the area here of the joint, where the objective here is, of course, to investigate the fatigue performance. And when we talk about joints, we don't talk anymore about purely life of the joint, but we want to see also how the damage progresses. And damage in a joint is usually a crack that is initiated either artificially or physically, and without any pre-crack in several locations. It might start here, it might start there, it might start there, it might start there, wherever. And we need to follow this crack propagation. And that's why we used, in this case, these crack propagation gauges. Actually, these are gauges like the normal strain gauges, but they work in a different way. They have wires, vertical wires like that. And when the crack goes, it cuts a wire. It changes the electrical signal, and that's why this is how we measure the crack propagation. So we did this testing in a lot of different types of loading. As we said before, we measured the crack propagation with cycles. The crack initiated here and propagated with cycles in this trend, a kind of linear trend up to failure. And also we created SN curves. And we again saw that these SN curves can be fitted by typical power law equations. I will discuss later on about this stiffness reduction. It's another type of SN curve that we introduced. So we did also durability analysis, which means that we did again fatigue testing, but for specimens that were preconditioned, specimens at minus 35 degrees, very cold conditions, Swiss conditions, temperatures and conditions at typical laboratory conditions, 23 degrees and 50% relative humidity, and at higher temperatures but the same humidity levels, and at higher temperatures and specimens immersed in water. And we've seen quite different result. In the first case, we had a fire tear failure, which means that the crack was initiated randomly, but then it was always switching to the first layer. If you see here, the failure is always in the layer of the adhesive. It's not in the composite, and it's not in the interface, except for the case of where we had a lot of water, this 40 degrees and 90% relative humidity, where we had an adhesive failure. So this humidity, so this water, led to adhesive debonding. So this is the adhesive failure means between the adhesive and the composite. So typical stiffness degradation, as before, very few stiffness degradation. You see it was only 5 to 7, 8% until failure. And of course, the expected, if you want, behavior with the environmental conditions, where we have the best case scenario, the specimens tested at minus 35, then 23, then 40 without water, and then the worst case was this case where we had 40 degrees and 90% relative humidity. And I'm coming back to this discussion. We are like that. This is 40 degrees, and above 40 degrees, we start having problems. And this is why this red curve is lower than the other two. And the 90 is because of the water intake that led to this failure of the interface. So
I have a question in the
yes.
previous. When you did the conditioning, the complete specimen was conditioned, not the adhesive part alone, I believe. Am I right?
The complete specimen was in either a specific temperature or in water.
Okay, thank you.
And then, so the conditioning has been done on the specimen in advance. The testing was done in an environmental chamber, but without conditioning. So the specimen that had 90% water was not tested in water.
Yeah, okay.
It was preconditioned there, and then the test was done in normal conditions.
Ambient.
With exactly ambient conditions. Okay.
Yeah.
So the fatigue testing continued with block loading and variable amplitude loading. And we had also the block loading, we applied tensile loading and compressive loading. And what is very, very interesting here is to see that in tensile loading, we had the typical failure of cracks propagating along the bond line in both sides. This was a secondary failure after the failure of the main, the basic failure here. We had this secondary failure. But then when we go to compressive failure, you see that the material started failing in the middle of the. So here we had, I didn't describe the material before, but the adherents that were used were peltruded elements that had in the middle unidirectional layers. So actually here the material failed in a mode 1 condition of this internal layer. And this was because of due to the compression, these two elements buckled and open like this. And the interesting thing is that the mode 1 fracture behavior of the adhesive, so at this region where we have the adhesive joint and at this region, was much better than the mode 1 performance of the adherent itself, so the composite itself. And this is the reason for having the failure, so the crack initiated in the middle instead of initiating somewhere in the edges. So we did also the fatigue data analysis. Again, I repeat, plots that are relevant to any other type of material, stiffness degradation that is similar to other types of material, and then the constant life diagrams that, again, here we see that the typical Goodman diagram that is shown here is not valid for this material. It underestimates the behavior in compression and overestimates the behavior in tension. And we have also the typical damage parameters here. So we perform more testing. I talk about a lot of testing for mean load effects. We created actually how many? 3, 6, 9 SN curves at different loading conditions, and established this piecewise linear constant life diagram, which is of course accurate because it uses all the fatigue data. Coming back to the discussion that we had before, regions that are closer to R equal to 1, so these regions and these regions are regions where we have creep-dominated fatigue. Regions that are around 0.1 or 10 are more fatigue-dominated fatigue. And this is the case where we have reverse loading, plus and minus at 0. Theoretically, this is a case where we have alternative loads over above and below 0 mean stress. Theoretically, this is the pure fatigue condition. Although, if you can, okay, we can say that this is the pure fatigue condition where we have a 0 mean stress.
I have one observation. When it comes to the compression, in the previous slide, you have shown that it's buckling is the mode of failure. It is. Yeah.
Yes.
So it is not the really adhesive fatigue. It is. Then can we correlate that as adhesive fatigue, because it is sealed? You are showing it as a compression failure. But if I change the specimen material, the substrate material, then the loads of failure will be different in that case.
Yes.
So then can we say that it is the substrate, it's not the adhesive which is failing?
I will respond in a different way. The specimen that we tested in fatigue, the idea was to avoid any buckling. So the specimen in fatigue had already a smaller material here. The tensile specimen was longer. So the tensile specimen, if I draw it here in the same way, it was like that. It was fixed here. And the compression, for compression, we avoid buckling here. And we didn't also have failure in this area because of buckling. So it buckled here, but it didn't fail. So the idea was to see how the joint, so the investigation for us is the joint area. And we wanted to see how the joint behaves in compression. And in compression, you don't have the other way to do this test instead of performing a test like that. What we could do, for example, to follow your suggestion, was to make here a very stiff element that doesn't buckle also. And then it would be a pure compression. So what we have here is not a pure compression. I agree with you. But we saw what happens in the joint, because the joint itself is a joint that is compressed. And when the joint is compressed, we had actually bending moments here because of this opening, and we had this mode 1 that happened. It's not a pure compression. I'm with you on that.
Okay, thank you so much.
So this is, with this I summarized. The conclusion is, as we said before, that we have measured techniques for everything, and we have common methods to simulate material behavior independent of the material system, and more or less all materials this is what we can also keep in mind, follow the same trends. The SN curve is more or less a power curve on the SN plane. The stiffness degradation has this behavior of sigmoid degradation up to the end. The constant life diagrams are not Goodman-like diagrams, but are, depending on the material system, might be more tension dominated or compression dominated, and so on. So this is very nice for us, because with that we can understand that the material modeling is becoming easier in this sense. We don't have to create a model per se for each material system, but we need to adapt actually the model parameters for any material combination. Okay, so with this we can have a very short break if you like, and then at the next discussion we'll start talking about, this is what we were just discussing now. We'll talk about the statistical analysis of fatigue data. It's a brief.
We can take a break for maybe 5 minutes. And
yes,
then
5 minutes.
Then you can reconnect
and share again. Maybe this one. Yes, statistical